Here I'm looking at the data booklet for topic 8, energy, power and climate change. The first formula, power is equal to a half A, this is rho V cubed, is specifically dealing with wind power. So you can only use it with wind power, where A is the area of the wind turbine, and that is usually given by pi r squared is equal to that area. The rho here is your density, and remember that is given by mass over volume. And V is the V cubed, the V is the speed or the velocity of the wind, speed of the wind. So that's that first formula. Looking at our second formula here, this is dealing with wave power, where A is here is the amplitude of the wave, and remember that amplitude is half the total wave. So if we've got a wave like this, and this is your equilibrium point, this is your amplitude here. It's the total amount divided by 2. The rho again is your density of your water, so this again is density. This g over here is your acceleration due to gravity, 9.81 meters per second to the minus 2, and your v is your velocity. This I here is intensity. That's the intensity of the light, and it's equal to the power per unit area. So your intensity is a watt per meter squared value. Here we have albedo. It's equal to the total scattered power or reflected power divided by the total incoming power. So it's a fraction. It's got no unit, obviously, because it's going to be a watt divided by a watt, and it will cancel. And it's a value from 0 to 1. This formula over here gives us the surface specific heat capacity. And I'd like to just go over here. It's defined over here. It's the energy required to raise the temperature of a unit area of a planet's surface by 1 Kelvin. So it's the energy, the Q here is your energy required. This is the surface area, this is the area, and this is the change in temperature. And usually we measure that in Kelvin or degrees Celsius. And this over here is your surface specific heat capacity. Here we have Stefan Boltzmann's law. This is to deal with black body radiation, perfect emitters, and the power radiated is proportional to the fourth power of the temperature in Kelvin. So this is Stefan Boltzmann's constant. You can find that in the data booklet. This is a constant, Stefan Boltzmann's constant. This is the surface area. And usually we're dealing with spheres, so that surface area is given by 4 pi r squared. Need to know that formula. And this temperature here, you must use Kelvin. It's a Kelvin temperature. Here we have the formula, which is basically the same as this, except that we've got the E, which is the emissivity, and that is given here. It's the ratio of the power emitted by an object to the power emitted by a black body. So not all objects are black body radiators, and that they don't all are not perfect emitters. So this E is again is a fraction. So basically what it is, it's the power of the emitter divided by the power of a black body, and that will give us our E value. Now that E value can go from 0, which is a very poor emitter and doesn't emit energy at all, to 1. 1 is where you would be black body radiation. And finally we have here, as far as our data booklet, we have our change in temperature can be calculated for a surface, for a specific surface, by seeing the energy coming in per unit area minus the energy being reflected or radiated out times by the time. This is the time that this is acting on it, divided by the surface specific heat capacity. So this over here basically gives us a delta Q, or a Q value. Gives us a Q value, and here we get, it's basically a variation of this formula, and this over here is your surface specific heat capacity. One other formula that isn't given, but I'd like to just mention it is important, is the coefficient of volume expansion. And this is the fractional change in volume per degree change in temperature. So basically it is that it's given by gamma, and it's equal to the change in volume divided by the total volume, divided again by the change in temperature. So it's a fraction, or how much the volume has changed, divided by per degree Celsius or per Kelvin.